Let's look at the picture one more time. Actually, we talked about this a lot of time, but this is a nicer picture. If you take E124, I'm also talking about this. Transistor is nothing but just the gate try to control the current from 1 to 2. The gate try to control the current from source to drain. Okay? Now, this is the band diagram I drawn to you before, right? When the gate is 0, I have a barrier, right? If you have negative bias, you make the barrier higher. If not, then we will go down, right? Then you have the conduction. Now, when this is what I'm saying, then you have the conduction, right? When you go down, then you can conduct. So transistor is a gate control resistor. Right? Any question about this picture? Source, drain, channel, metal, right? Now what happened if we try to do the scaling? The drain is going to have some control on our gate, because when you have a very short channel, you see that I parallelly shift this one to here. I shift it parallelly. Short LG. And this becomes the drain. Then do you see that the barrier is smaller? And that's why you have smaller VTH, because for the same VG, you actually have lower barrier. And this is the VTH roll off, right? And on the other hand, if I have a very, very large drain voltage, right? I have an even smaller barrier. For the same VG equal to 0. You see, I keep pulling down the barrier. That is the dipole. Okay? And this is what we said last time, right? About this shifting of the threshold voltage. And you see that if we have a dipole, right? For example, from here to here, originally from here to here, it was 0.5 volt. Now it becomes 1.1 volt. You have this. Then the leakage current will be many times larger. Here is 1, 2, 3. 1,000 times, 10 to the power 3 times larger. Any questions? Any comment?
Can you explain that graph again, why it's larger?
Now, this is what? This is the IDVD when the VD is 0.5 for low, let's say just for low 0 VD, right? This may be VD, let's say equal to 0.05 volt. And this is the, let's say I don't want to mess up with this 0.5, 0.2. Let me use another number, right? VD equals to 2 volt. Now at 0 bias, this is VG equal to 0. Do you see that this is the current for this guy, and this is the current for this guy, right? So the I off increased about 1,000 times. The off state current. Is that okay? Do I answer your question?
And that's because of the smaller barrier?
Because of the smaller barrier, you're right.
Okay, thank you.
So originally you have this. Maybe I should not do that. Originally you have this. 0.05 volt. And then you pull it down, right? You just think it as a string. 1 volt. The electron see a smaller barrier, correct? Both of them has Vg equals to 0 volt. Okay? Any questions?
And that red line is the VD to 1 volt?
Vd equal to 1 volt, Vd equal to 0.05 volt, right? Because this is source, this is drain, and this is gate. Make sense?
Yep, thanks.
Great, okay. So last time we talked about the charge sharing model, right? So how do we calculate the change of the threshold voltage? We say that, hey, the reason that the drain gain control is because it has some extra depletion charge sustained by the drain. Originally, in my 1D model, all this depletion charge under the gate are supported by the gate voltage. So you need to increase the gate voltage in order to form a full depletion layer. But now the drain already forms partially for me, and this is this area, right? So if you try to use geometry, you can come up with this equation. You find that the change in the voltage is just the change of this delta Q, delta dQ divided by C ox. Okay, it just said I need to think about this. It is just a tape. You want to turn it on, right? The tape, let's say the tape, in order to turn it on, you need to twist by 90 degrees, for example. But now someone, which is the drain, somehow help you to twist by, to turn it by 10 degrees already. All you need to do is just change it by 90 degrees. Then you say, oh, the threshold voltage is reduced, right? I need less effort to turn on the transistor. And that is what we get. Okay? We don't need to memorize the equation, but very important, we want to see if this is the same with our intuition. How can you avoid short channel effect? We know that we need to make L very large, right? Because that is what we mean by not short channel. Short channel is the channel being very small, right? But how large is large? This equation tells us that L has to be much larger than Wm, right? Why? So that Wm divided by L is almost 0. That means delta Vt is almost 0. Delta is talking about the change of Vt. Right? So if I can make L much larger than Wm, then basically there's no short channel effect. Right? That's good. That is what we expect, right? But this gives one more insight. Before we just say that here, we just say that I want the channel to be long. But how long? 1 kilometer? No. As long as it is longer than the depletion width, then it will be good. Okay? This is a very simple model, but very intuitive model, pretty useful model. Okay? And it is derived by assuming T-ox equal to 0. You see that the T-ox does not come into play. You see no dependence on T-ox. The thickness of the oxide, this is T-ox. Okay? And actually it is also wrong. You see that it only can capture short channel effect. It cannot capture dipole. Okay, and it also gives the wrong relationship. It looks like short channel effects goes down with 1 over L, but which is not true. Okay, but that is okay. The point is this is a simple model. Any question about this model? This is called charge sharing model, right? The drain help me to support some of the charge. I have less charge to support as a gate. Now, if no, then let's talk about the dipole one more time, right? I keep repeating, this is the purpose of the class. You come back and go so that you have this immersion, right? You immerse in this idea, keep repeating. Hopefully that can help your learning. On the left, this is the long channel. I already showed you, right? And you see that there is a barrier. This barrier determines the VTH, right? I hope you remember. I have drawn this curve to you earlier. What happened when you increase the VG? The barrier becomes smaller and smaller, right? When you increase VG, right? And as a result, your electron can go through. Remember that? So this barrier, this very tiny barrier, it will determine the VG. When it is a short channel, when it is a long channel, even I increase the voltage to 1 volt, let's say this is 0.1 volt. Now I increase it, because this is long, maybe it will be something like this. The barrier is not changed, right? Phi not changed. That's why you have the same VTH. But here it is different. Maybe I should not add this. Actually, it is in the graph already, right? This one was 0.1 volt, the dash 9. And then this becomes 1 volt. And you see that the barrier does not change. But when you have a short LG, you start with 0.1 volt here, and then become 1 volt. You see that it's difficult to see, but you see it here. Smaller barrier. Smaller barrier means lower VTH. Is that okay? And what happened to the subthreshold swing? It also gets worse. That is the question you asked in the Piazza, right? In the extreme case, we already showed that you have a worse subthreshold swing. Why? Because the gate has less control on the channel. Okay, so this is the picture, right? Try to understand this picture, or even memorize this picture. Is that okay? Right, I just repeat what I said in the 2 slides before. Right? Try to have the feeling that when I apply positive charge on the drain, I pull down the band. How much can I pull down? If it is so short, I don't just pull down here, I actually affect this barrier, make it down, right? So it's very intuitive, right? So why do I say this? Because I want to remind you that the barrier determines the threshold voltage. So here we come to the second theory, polynomial potential method. Don't worry about all this equation. This is just for your information, right? What it is trying to do here is that let me solve the Poisson equation. This is the Poisson equation. If I solve the Poisson equation, I will know what's going on, right? I can find out the barrier, right? So in this polynomial method, they assume that at the surface, the potential is only a function of x in polynomial. And then the coefficient is a function of y. X is in this direction, y is in this direction. Okay? And they apply the boundary condition, and then they solve it. Right? You see, I go very fast. I'm not going to solve with you. You don't need to solve it. If you like that, it will be great. You try to follow the paper to solve it. But the main point is this. They derive, this is the result. And you also don't need to memorize this equation on in the cheat sheet. But it tells us that the change of the barrier has this form, e to the power negative L divided by LOA. What does it mean? What happens if L is much larger than LOA? What happened to the term? What is phi mean when L is much larger than LOA?
Reduced to A1.
Becomes A1. Because e to the power negative a big number is 0, right? Then it means basically there's no VTH roll off. There's no VTH roll off in this case. Okay? But it's impossible, right, to make it very large. I mean, we can make it very large, but useless, right? So here, what is A1? What is LA0? This is the equation it is given. Still wrong. But it introduced a very important concept called scaling length. For a technology, if you want to be scalable, right, you want to have a L larger than, for example, L at least larger than 3 LOA. Because when it is larger than 3 LOA, it's e to the power minus 3. Then that gives you a small number. Okay, and then from here we can study. Can you tell me, you want, for a good technology, do you want a long scaling length or a short scaling length? Do you want LOA to be short or long in order to scale?
What is LOA again?
LOA is a constant given by this equation. And we say that when the channel length is larger than LOA, this term will be 0. Then you have no threshold voltage roll off. So this term tells us the change of the, this one tells us the delta, you can say delta phi or delta VTH. It tells us the change of the threshold voltage, right? So if we can make the channel larger than LOA, then we don't have, that is, no short channel effect, right? If your length, let's say 1 micron, and LA is 0.1 micron, your length is much larger than the LOA, so you don't have short channel effect. Now, do you want to have a small or large LOA for a good technology? First of all, do you want to have short channel effect?
No.
No, you don't want to have short channel effect. If you don't want to have short channel effect, should the gate length larger or smaller than LOA?
Larger.
Larger, very good, right? Then from absolute point of view, do you want LOA to be small or large?
Small.
Small, very good, right? Because if your, I kind of running out of space, sorry for that, right? Okay, my internet was not stable, right? But the point is you want to have a smaller LOA, right? Need smaller LOA. So can have smaller LG while you don't have short channel effect, right? If my LAOA is 0, then I can scale my device to arbitrarily small. I still don't have short channel effect. Okay? But what's the point here, right? LOA, yeah, you give me the equation. Then what insights can we get from here? I want to have small LOA. How can I achieve small LOA based on this equation? Can you tell me? How can I achieve small LOA? How can I make this one small? Someone tell me? Well, to make it small, I want WDM to be small. It means I want to have a very small depletion width. Wow, this is consistent to what we said earlier. We want to have a small depletion width compared to the gate length. What else? What else do we need to have a small LOA? From here, which one can make my LOA small? Can you hear me, by the way? My internet had problem. Anyone? Can you hear me? Just let me know if you can hear me.
Yeah, we can hear you.
Okay, now you answer. What else? Which term?
See the oxide, the oxide epsilon.
Oxide. Very good. Oxide. You want it to be small or large?
You want it to be large.
This is a little bit confusing, right? You both have in the denominator and numerator, right? So let's assume that this term, the second term, can be ignored because oxide usually is smaller than the WDM. Then you actually want it to be small, right? So you are right, but it really depends which term dominates. Okay? Because you want this one to be small and this one to be small. But why do I need this equation? Well, you can put in cheat sheet, but the point is, this gives us the intuition. We need a small oxide. Make the gate capacitance large. It makes sense because I want to control my device. I want to control it. So I make the capacitance large by reducing the T-ops. I also need to have less depletion because if I have smaller depletion width, just like here, I have less encroachment. I have less charge sharing. Is that okay? Any questions? If not, then let's go to the next page, right? Here, I try to show you the fitting of this polynomial potential model, which is the theory two, right? They solve the Poisson equation, assume the Poisson equation has a polynomial form. Eventually, they find out what is the reduction in the barrier, and they come up with the scaling length. This paper, what they are saying actually are wrong, okay? They cannot be used in arbitrary case, but they are good because they introduce something called scaling length for the technology. And here shows the change of the threshold voltage as you reduce the gate length for different bias. The dot are the 2D simulation, the 9 are the model, and you see that they fit pretty well, right? Of course, if they don't fit well, they don't submit the paper, right? But anyway, but there's a problem for this polynomial method. you see that actually the equation they are saying is only satisfied at x equal to 0, means at the interface, okay? They make a lot of assumption. They also assume that there's a constant vertical electric field in the oxide when they apply the boundary condition, right? We can skip this, I don't ask you to do that, but from here you see that they just assume that the oxide potential across the here is constant, but in reality it is not. In reality, this is the electric field. If this is the oxide, right? They assume I have constant electric field in the oxide, but in reality, no, I have fringing field here because of the 2D effect. So here is not constant. And this has more problem when you go to shorter channel. Okay. And then if just now we say that if we have T-ox, we want the T-ox to be small, right? But when the T-ox is large, when they are large, then this term will cancel, right? When I have very large T-ox, then the T-ox will got cancelled also. Then it's independence of T-ox, independence of the thickness of the oxide when the oxide is large, which is wrong. When the oxide thickness is large, it still depends on the T-ox. So that is the problem. You don't have to memorize this. Who will memorize this, right? But I still want you, when you study, go through this, because then you understand how the importance of this channel length is. And then you know how to analyze this equation, right? I can give you another scaling length equation in the exam, and you need to analyze and tell me whether you want to make it small, right? Whether it makes sense, right? Whether it's counter your intuition or whatever. Is that okay? Now, so this is not good. Then people come up with another theory. The equation even longer. I don't bother to put in the slides. But the main point is this. They try to solve the Poisson equation. But when they solve the Poisson equation, right? Why do they solve Poisson equation? Because they need to find out the barrier lowering, right? They want to see how much barrier is changed. That is what we are talking about here, right? The delta barrier, right? How much is lower? That's why you need to solve Poisson equation. But solving Poisson equation is very difficult because you have two regions. One is the oxide, which has epsilon equal to 3.9. Another is the silicon with equal to 11.7. It's difficult. So what did they do? What did they do is they just increase the oxide thickness by 3 times. Not really 3 times. When they solve the equation, by 11.7, thickness, the thickness, right, becomes T-ox times 11.7 divided by 3.9. Increase it according to this, and then we put the permittivity as 11.7. Here also put 11.7. This is not exactly correct, but they solve this and then they get this equation. The reason we make it larger is why? Because we want to keep the same capacitor. Remember, the capacitor is equal to epsilon divided by T-ox. By doing this, it is constant. We did not change the oxide capacitance, right? Because I make it thicker and the dielectrical constant goes up also, then the capacitance is the same. And they come up with this. Now, the question is, does this make sense? Same as this, right? We want smaller LOG this is the scaling length, right? Remember, the scaling length is that if your gate length is larger than the scaling length, then you can scale it without short channel effect. I have connection problem again. Let me say again. The scaling length is that when your gate length is larger than the scaling length, then you don't have short channel effect, right? Your gate length need to be larger than scaling length. So that's why you make the scaling length very small. Then you can keep scaling, right? If your scaling length is 1 nanometer, I can scale to 10 nanometer, 5 nanometer. If your scaling length is 1 micron, I cannot go lower than 1 micron, because if it's lower than 1 micron, I have short channel effect. How can I make it smaller? You see, it's the same. I need to reduce the depression width and also reduce the T-ops. Make sense? At the same time, I can increase the epsilon of the oxide, and that is related to the so-called high K dielectric. And it all makes sense because we're talking about the control. The gates want to control the channel. What I'm doing here with T-ox and epsilon ox is to increase the capacitance, right? Any questions? But this is still not correct, okay? So eventually, there's a way. Let's just solve the Poisson equation in both oxide and silicon, but still using 3.9 or the dielectric constant in the oxide. We don't scale it like here, right? We don't scale the structure accordingly. So that's why we do that, right? And that becomes very complicated. It doesn't have explicit form, but you come up with an equation like this. You say that the scaling length, the depression width, the T-ox have to satisfy this equation, okay? And then we can plot them here on the right. On the right, we plot the depression width. We scale it by scaling length. On the vertical axis, we plot by T-ox, scale by scaling length. And then each of these is a solution. For different epsilon OX divided by epsilon SI. Any question about this plot, right? So maybe it's confusing. We solve the equation. Don't worry about how they solve it. They just tell us that eventually your scaling length, your T-ox, your depression width, your dielectric constants have to satisfy this equation, right? Then you can solve it numerically, or we can just plot on a graph, right? So they plot you to the graph. Each of these line is a solution. For example, if your epsilon ox divided by epsilon silicon is 1/3, which is silicon over silicon dioxide on silicon, then you have this curve. This is the solution. It means that if your WD is here, then your T-ox is here. They satisfy this equation. Any questions? Can you hear me? No, no one want to answer.
Yes.
Okay, I'm not asking questions, so don't worry. Okay, so what is the point? Now, the main point is that we are sure that you will see this in assignment, right? And maybe even midterm. So please pay attention. How do we get the solution, right? So for example, now I have a transistor. Let's try to understand what it says. Epsilon silicon equal to 11.7. This is just the silicon, okay? And then I have a gate oxide. It is 7.8. So this is not silicon dioxide. It is actually silicon nitride, okay? And then I say that the oxide thickness is 5 nanometer, okay? So this is the gate, source, drain, and the depletion width is 10 nanometer. Do you understand the question? Any problem about this question? And you want to find, question is, find the scaling length. Okay, how do you find the scaling length? Now, I know that, first of all, right, I know that it will be on one of this curve. Okay, and also I know already what is Ti divided by WD. 5.0 divided by 10.0 equals to 1/2, right? So this is Ti, this is WD. So it means what? It means I will have this slope. So all the solution must lie on this point because the Ti divided by WD must be 1/2. That is one thing, right? Second thing is I need a curve that represents this ratio. This one is equal to 7.8 divided by 11.7. It's about 2/3. This is 1/2, 1/3. This is 1. So the curve must be somewhere like this. Right? So this is the curve of epsilon I divided by epsilon Si equal to 7.8 divided by 11.7, 2/3. Okay? And then I will say that it must be, the solution is the intersection of this line, this straight line, and this curve, right? So I take this point, right? And then I can read out from here to find out what is the 2 pi. For example, 2 pi, here I get 2 pi WDM divided by LOI equals to about 0.63, right? Just read off from here. And then I do some manipulation, I get LOI equal to 10 nanometer. Then it means that this technology has a scaling length of 10 nanometer. So what is the minimum transistor I can build so that it still don't have short channel effect? It is about 3 times, right? I don't know if I emphasize enough, but here I say that for this theory, or most of the theory, you want the minimum transistor length equals to 3 times of the scaling length. So the smallest transistor I can make without short channel effect is 30 nanometer in this technology. Well, I give you 1 minute to think about what I have been talking. Please let me know if you have any questions.
Hello, Professor.
Uh-huh.
Can you just go through the process once?
Okay, yeah, I'll go over the process, but can you help me?
Yes, Professor.
Okay, now, first of all, we are given this technology. Okay, you have fabrication process. You have the epsilon, the substrate is 11.7, right? Epsilon, the oxide is 7.8. T-ox is 5 nanometer, depletion is 10 nanometer. That's what I drawn here. Is that okay for this part?
Yes, Professor.
Yeah. Now the goal is this. We know that this equation tells us the relationship between all the process parameter and the scaling length. You can solve it, right? But they are not in explicit form. That's why we draw this curve. Each of these curves corresponding to 1 epsilon I divided by epsilon Si, right? For example, if the oxide is 10 times the permittivity of the silicon, then the solution of that equation fall along this curve. The solution, it can be any point. It depends on what is the actual thickness of the WDM. Is this part okay? How we have this curve?
Yes, Professor.
Okay. Now, then the point is, we know that what is Ti divided by WDM, right? This is a scale version of them, but still this is just Ti, this is WDM. They scale together. So if I draw this line, the intercept of this line and the curve will be the solution. Does that make sense?
Yes.
Okay, good. And now, the point is I need to find the right curve. In this case, I only given this 4 curve, but that is not what I want. I need a curve that is 2 divided by 3 with epsilon I divided by epsilon silicon. So I sketch it by interpolation, right? This is not a good interpolation, but I sketch it. Or maybe if turn out that you are given 3, then you just use this curve, right? So this interpolation, are you okay with this?
Yes, Professor. So basically, it's a curve of epsilon I upon epsilon Si, right?
Yeah, for each curve, they correspond to different epsilon I divided by epsilon Si.
Okay, so for the case that we are considering now, it has 2 upon 3.
Yeah, it runs 2 over 3, but we did not give you this curve. So you guess, you sketch, you say, oh, this may be approximately this one, right? Because it's between 1 and 1 over 3.
Okay, Professor.
Okay? And then the solution is the intersection between this curve and this line. Is that okay?
Yes, Professor.
Yeah. And from here, then I know what is WD. Of course, I know it's not exactly W, it's 2 divided by pi WD divided by OI, right? Equal to about 0.63. That's how I get it, 0.63. And with this, I can find what is LOI. So what I'm doing is nothing but just solving for LOI when I know this 4 quantity, this 5 quantity, this 4 quantity, right? I know epsilon OX, TOX, epsilon SI, WDM. And I can solve for it, but I just use graphical method to solve for it. I got LOI. The LOI is 10 nanometer. And then, so that technology has a scaling length of 10 nanometer. And as I said, right, if you are 3 times larger than the scaling length, your transistor will work well. It won't have short channel effect. It's just like I give you a process and then you say, I want to draw a 1 nanometer transistor. It won't work. It will just shorter because of short channel effect. But if I tell you that my process has a LOI of 10 nanometer, then you say, okay, let me draw 13 nanometer. I'm sure that there will be no short channel effect, and this is my typo. This is with no short channel effect. Make sense? Do I answer your question? Feel free
Yes,
to
Professor.
ask. Huh? Okay.
Just one more question. The line that we have drawn from, that starts from 0, like the point that the intersection. So what is it exactly?
It is just telling you the relationship between Ti divided by this slope is just equal to Ti divided by WDM. The slope,
Okay.
right?
Okay,
Because
Professor.
Ti is Y, WDM is X. So this slope is just equal to Ti divided by Wm. Right? Because I cannot draw others. For example, let me draw this one. And can I claim this as my solution? No, because at this point, Ti divided by Wm is not 1 over 2. I need it to be 1 over 2 because it is given to be 1 over 2.
Okay, okay, Professor. That's pretty clear.
Okay.
Yes.
Yeah, thanks for asking, right? This is very important. Any other questions?
No, Professor.
Okay. Other people? No, so try to practice. You have this in your assignment, okay? Okay, another theory, right? Why I need so many theory? Because we want to appreciate the different methodology. You see that many of them are wrong, but they have insight. So here is another thing called voltage doping transformation model. Ignore, you can forget the name. I don't ask you to remember the name. But this one gives us something very useful. It separates the short channel effect into the VTH roll off. So here is a little bit confusing. This means VTH roll off due to LG. Okay? Okay, my connection has problem again. So let me say again. This one refer to VTH roll off due to LG. And he introduced something very important called electrical integrity. Okay, so your final threshold voltage is just the original threshold voltage, means the LG equals to infinity. Subtract these two numbers. You give me all this quantity, I will know that. I will know the result. And it is easier to compare across technology. First, are you okay? Don't look at the equation first. Are you okay with what I'm saying? Why we have this? We have a new model. This model tells us how much threshold voltage change is due to VTH roll off and how much is due to the dipole. And how to calculate it is here. And they share the same something called EI, electrical integrity. This is important. We can use it to compare different technologies. When we say technology, it means, for example, planar versus SOI versus FinFET. Let's say 3D transistor. Okay, now let's take a look at this one, right? Maybe let's do this, right? How do we improve the electrical integrity? What we try to do is this. This is the so-called bulk FinFET, bulk transistor. You have source here, you have the drain here. Correct, right? So let's write down what is the electrical integrity from the last slide. EI equals to 1 plus xj squared divided by LEL squared times Tox divided by LEL times T depletion divided by LEL. LEL is nothing but just the gate length. It is electrical gate length, but let's just call it gate length for simplicity. Do you know what is xj? Do you know what is xj? Junction depth. What is xj? This is xj. Does it make sense? When you have a deeper junction, you have a deeper drain, your gate has less control because here the drain can try to control your channel like this. Your gate is far away. It's more difficult to control, right? T depletion basically is just the WDM, the depletion width. So we want to have a small EL. Can you tell me, how can I make the EL small? Look at this. If it is small, if the EL is small, the threshold voltage reduction due to the roll off or dipole is small. So we want it to be small. Someone tell me, how can I make the EL small from this equation? Can you hear me?
You increase the length.
Very good. What else? How can I make EL small from the equation?
Oxide thickness.
Say again.
Oxide thickness. This is
Oxide thickness. What do you want to do with the oxide thickness?
Reduce the junction depth.
decrease.
Decrease. What else?
Yeah, less junction depth.
Less junction depth. What else? Maybe you cannot see this of my writing. What should we do to T depression? Reduce. Correct? And these are all we have been doing. This is correct, right? Make the channel length longer, then you don't have short channel effect. Make the gate oxide smaller, you have good gate control. Make the junction depth smaller. In principle, it means you increase the doping, you reduce the depression width, right? Same, reduce the depression width, right? So that is what we need to do. How can we do that? We actually can do this with other devices also. We'll go into the details later, but now we can actually see some of them. Hey, this is the junction depth, right? And this is the depression width. How can I make it small? I just insert an oxide here. Do you see that? I insert the oxide here. This is the junction depth now, smaller. This is the depression width now, smaller, because I make it very thin. Okay? What if I have another gate, what we call double gate? Basically, because you have two gates, I can use symmetric method. I say now the junction depth is only half. The depression width is also only half. So this is even better in terms of electrical integrity. I have even smaller threshold roll-off. Right? In this method, we don't have the so-called scaling length, but it gives us the absolute value of the roll-off. Make sense? Any questions? Right? So we come up with all this idea is based on some theory. We don't just say go to SOI, silicon insulator, go to double gate. It has some implication. By SOI, we can just cap the junction depth by using this. Cap the depression width by having an oxide blocking the depression width. Right? Double gate, we make it symmetric. We reduce them into half. And that is what we have here. If we look at here, this is the original electrical integrity. When we go to so-called fully depleted SOI, I don't discuss now, the equation is changed. Why? And what is changed? First, this is the thickness of the silicon. This is silicon, and this is oxide. Now it becomes Xj. The Xj becomes Si squared. It is smaller. Depression width now becomes Si. However, not exactly Si. It also depends on the thickness of the box, just because of the field penetration into the box, right? Because into the berry layer, into the berry oxide layer, right? Because your electric field does not stop right away. It has some effective penetration. So effective depletion width is a little bit larger. And now if I go to double gate, this one is just the TSI divided by 2 because I need to take the symmetric, right? If I do the symmetric view, then both the depletion width, this is T depletion, and the junction depth is reduced by half because I get control by 2 gates. This is gate 1, this is gate 2. Any question about this? Okay, right. So if not, then we also have other theory, right? This is from, we look at theory 4 as a comparison, but this is just for SOI, silicon on insulator. We will discuss more later. Basically, it means you actually have a very thin layer of silicon on top and then put the oxide on the bottom so that there will be no current flowing through this oxide. Then you have a very good control of your device. Right? This is the gate, this is source, this is drain. Right? This is the silicon on insulator. Right? If we have a single gate, it has this equation. When you have a double gate, right, you see that you just reduce this by half because effectively the thickness is reduced by half. We also have quadruple gates. What does it mean? Then you need to think it in a 3-dimensional way, right? This is source, this is drain, and then you have the gates, gate 1, gate 2, and then surrounding it. So basically it's reduced by 4. And this is the scaling length that we are talking about. Right? So if we can add more gates to it, we have a better gate control, then we can scale the transistor even smaller. Right? This is another theory. So now we know that basically